Okay, this is section 6.2. This is a system of differential equations, homogeneous system, I guess, of differential equations. Okay, so this is just a second example, and again, it's a homogeneous system. So suppose we have something like x prime of t is equal to I think it's 2x of t plus 3y of t, and we're told that x of 0 is 0, and then y prime of t is equal to 2x of t plus y of t. And y of 0 is equal to 10. Okay, so the basic methodology we go through to solve this, and this is assuming distinct eigenvalues. We won't worry about, what if they're what if you get the same eigenvalue in multiplicity 2 for differential equations, but let's look at this. So our first step is we determine our matrix that we want to work with. Okay. Then we get the eigenvalues and corresponding eigenvectors. Okay. Then from those eigenvectors, we create P and P inverse, or find P inverse, so that we have that. And then what we know is our solution x of t, y of t is equal to, so I'm going to set it as vector like that, is equal to P times x1 of t, y1 of t. Okay, but what are those? Well, those were the simpler differential equations, the uncoupled differential equations. So this is P times, and this is x1 of 0 e to the lambda 1t, and y1 of 0 e to the lambda 2t. Now then, we also have to get our then x1 of 0 and y1 of 0, and that was P inverse times x1, not x1, but just x of 0, y of 0. So those were the steps we needed to follow. And once we had that, then we had our solution. So, okay, let's look back here. Let's get our matrix, 2, 3, 2, 1. So our matrix we want to work with, A, is 2, 3, 2, 1. And so we need to get the eigenvalues and eigenvector of that thing. So I need the determinant of 2 minus lambda, 3 to 1 minus lambda. That is lambda minus 2 times lambda minus 1. It's easier for me to do the multiplication that way. And then minus 6. So this is lambda squared minus 3 lambda plus 2 minus 6. So that'll give us a minus 4. So that's lambda squared minus 3 lambda minus 4 is equal to 0. So that tells us, that tells us lambda is equal to either 4. Let's see, so actually I think I'll do it in the other order. So our lambda 1 is equal to negative 1, and lambda 2 is equal to 4 when we factor that thing. So, right, we have, I should have probably added one more step in there and said that's lambda minus 4 times lambda plus 1, and that we set equal to 0. So we get those for our eigenvectors. And then eigenvalues. Okay, so I have, so here's for lambda 1 equal negative 1. I get a 3, 3, 2, 2. And when I augment that with 0, of course, I can easily see that disappears into zeros. And so this implies that x equals negative y. And so a perfectly good solution vector for that would be, say, 1 and negative 1. I could have also used negative 1 and 1, but we'll go with that. So there's x1. Oops, gotta be careful there. Yeah, sure, that's what they use. You just have to be careful. This x1 has the bar over it. It's a vector. It is not that x1 of t there. Okay, and then lambda 2 equal 4. And that was what again? 2 minus lambda, so we get a negative 2, 3, and a 2 and negative 3. And so once again, I see, yeah, that'll disappear just fine. And so what this says is 2x equals 3y. And so a quick, easy way to do that is just swap those coefficients. So in other words, let x be 2, x be 3, and y be 2, and I get that vector then. Okay, so there we have our eigenvalues and corresponding eigenvectors. So then let's create P and P inverse. So P is, what was that, 1 minus 1, 3, 2. And so P inverse, now, I could use Sage, I can do all kinds of things. I'm going to use the formula of 1 over the determinant. So I've got, 2 and plus 3, so 1 over 5. And then times the diagonal, main diagonal swapped, and change the signs on the off diagonal. And there we have P inverse. I could push the 5 through, the 1 over 5 through. I'm going to leave it like that. Okay, so we've got P and P inverse. Then 4, it says, oh, there's the solution. I need P times that thing. And so, okay. So my solution thus far is that x of t, y of t is equal to my p, so 1, 3, minus 1, 2, times my vector. Now this is x1 of 0. Now I could do this first. I could figure out x1 of 0 first and so forth, and that would be fine. Swapping 4 and 5 here. I could do that. Maybe I will. Maybe that'd be the thing to do. So I'm going to swap 4 and 5. So we'll come back to that. And we'll first figure out x1 of 0, y1 of 0. Well, that is just our p inverse, so 1/5, 2, -3, 1, 1, times our x of 0, y of 0, that was 0, 10, I think. 0, 10, right there. And that's a pretty easy thing to deal with. Right, I'll get a -30 in the top and a 10 in the bottom, but that's divided by 5. And so I get -6 and 2 from that multiplication. So there are those vectors. Now I'll go ahead and do that last step of x of t, y of t is equal to p. So that was, I crossed that out, 1, 3, -1, 2. 1, 3, -1, 2. Times my x of 0, which was -6. E to the lambda 1, so lambda 1 was -1. E to the negative t there. And then 2, e to the 4t, because lambda 2 was 4t, right? And so back here somewhere, there, that's our solution. Okay, so now I do that multiplication, and I get the vector -6 e to the negative t and 6, so plus 6 e to the 4t. And then bottom row here, I get a positive 6 e to the negative t and a 4, so plus 4 e to the 4t. And kind of checking quickly, if t equals 0, I do indeed get 0 for the top, and if t equals 0 on the bottom, I get 10. So there is my solution. Okay, so it's a pretty algorithmic sort of thing. You know, I find those eigenvalues, get the eigenvectors, produce the p's here, and then, you know, yeah, I would say probably it makes the most sense computationally to find the constants first here that we need, and then go ahead and multiply by p. Yeah, I think it saves a little bit in doing that. And so we do that, and where is it? We end up with our solution. So there we go. There's another example of a differential equation.